All right. Well, we are live now, so off you go. And I have already screwed. No, no, I'm already right. Okay, excellent. Well, not sure that anybody has had time because I've been ill. Sorry, everybody. I've been feeling quite unwell, so not been as organised as I might have wanted to be. Um, yeah. Okay. We've got concurrent viewers 0 according to the thing, but I'm not sure that. But I'm not sure that I believe that because somebody's commenting in the chat. Um, so it could be magic. So welcome to the third episode of Debunking Weekly. And again, for those who missed it, apologies. I've been feeling seriously under the weather and not at my best. So I apologise for being late. Anyway, today we're talking about light. Phil, what do you think about light? What would you like to say? Yep.
So that's in terms of photons, and then we'll talk about that don't understand.
Yeah. It is very, very annoying when they do that. Like, you guys haven't produced any evidence of anything, but we can make up a firmament. Yeah.
Right? Yeah, we just don't make,
Yeah.
and we provide evidence
Yeah.
for that. Be a photon based on the
Yeah.
one I have a look at is the characteristics of, as who's sort of done basic physics know particle duality. So what we're saying, and then also has wave, has you came out and just all objects resonate us. So it's not surprising evidence from Young's double slit experiment, which then
Actually, we've lost the stream. Okay, so okay, all right. So I think we're back. We ought to,
okay.
we certainly seem to be. So yeah. So we're back now. But yeah, I want to, you've gone through a list of sort of the properties of light. And we didn't just, one of the things you said, we have evidence for this. Yes, and that's key. We think about light in these ways. We have these ways of analyzing light because of the evidence, not the other way around. We didn't develop a theory in a dark room and then go out. Well, light must obey these properties. We determined the properties of light by looking at how light behaves in different circumstances, and
Yeah,
and
exactly.
it's the exact opposite of what the flat earthers do.
Every time you just say it, just makes me want to laugh.
Yeah, it is amazing that we're doing it. That we're treating this with any sort of seriousness. That we're even
Yeah.
spend that anybody is spending time even talking about this as errant nonsense. But yeah, so let's start with the first one.
Going to wipe the stuff off the board.
Yeah, okay.
Now I've sort of written down what was on it. We're going to cover. I sort of made a mistake and put some propanol on this thing, and
Now it just smears. Now it just stains everything.
Yeah, so it actually makes a bigger mess than usual. So I'm going to have to work out some other chemical because propanol. I think what happens is it leaves streaks of the material behind, and actually doesn't do the board much good. So I think I'll probably have to use just good old soap and water in the future. All right, so the first thing I think we had on our list was what is light?
Yep.
Okay, which is really quite a good question. So I think it'd probably worth just taking us back a little bit, because there's people out there who are interested in knowing. I don't know if our little friend Rachie is out there. She is
out there. Yep. She just arrived.
Okay. Yeah. Okay. Excellent. So we'll start first of all by saying, well, let's go right to the beginning and discuss, say, for instance, a sodium atom. Okay. So I'm going to use Rutherford's description of how atoms are. It would be pretty complex to draw what a sodium atom might look like in reality. With electrons whizzing everywhere. So let's just draw a representation of the different energy levels. So sodium, like all atoms, would have a nucleus, and this nucleus would comprise of protons which are positive, and they would have neutrons as well. Okay, neutrons which have no charge, zero charge. Okay. All right, so that would be a nucleus. So it's all about, if you like, the center of an atom. So around this center, we would have energy levels, and sodium has 11 electrons. Okay, so therefore the first two electrons occupy an energy state that we call the S1 and S2, and then after that we've got another 8 electrons in another energy state, so that's S2 P6. So there's 8 of them here. 1, 2, 3, 4, 5, 6. I've got 8 there. 1, 2, 3, 4, 5, 6, 7. I think now we have 8. Good. All right. So that's an energy shell that's complete. And then finally, we have this lone one out here, electron, and actually the very reason why sodium actually reacts with anything. It's not these electrons over here that are particularly interesting in terms of chemical reaction. It's this one, okay, this one out here. So the way this would work out would be, most of the time this electron would be in that sort of position. So if you had and looked at that, you would be able to see that most of the time this electron was there, and if you like, ready to react with other elements. Now, but what's important in terms of light is that we can give this some energy. So in other words, I could put this in a flame, I could heat it up, I could actually give this energy, and as I give this energy, what I'm doing is I'm causing this I can lose that altogether. Okay, and I could lose that to another element, like oxygen, for instance. Okay, I could lose that to another element, and each of these ones could be could raise up to another energy level. So they would raise up. So they were over here, for instance, at S1. They can move up, and as they move up because I've introduced energy. And what happens is, as a result of losing this energy, they come back to their ground state. So as they come back to their ground state, they give off photons. And this energy, remember, the energy is neither gained or lost. That energy is then released as photons. Okay, and now we know what's the evidence for it. Well, we can do this with, and we can see that the amount of energy that's released is proportional to the number of photons that's actually released from there. So the energy, we put in energy, we get energy out again, the energy is released, and we see that energy is proportional to the amount of photons that's released. Okay, so the number of photons times the wavelength times Planck's constant. Okay, so we can we can tell that. That's the evidence of it. So we didn't just make it up like the firmament. Okay, all right. Okay, the next thing is, so that's basically where a photon comes. So where does the photon from the sun come? What happens over there? Well, photons are created at the center of the sun. Now, when I talk about photons, I don't just mean visible light. I mean, in terms of the sun, we're talking about very, very high frequency. So I'll talk about that in a minute, about what they are.
Okay.
So the photons created at the center of the sun are gamma rays, which are very, very high frequency, high energy photons. For the same reason that this happens, because as hydrogen becomes helium, again, remember what I've said, for instance, getting rid of this electron, so hydrogen actually shares its two electrons, smashed together with another hydrogen, creates the new element helium. And as it does that, as it gets back to its normal state, releases this energy, okay, and this energy comes out as photons, as gamma rays. Now what happens is the sun is a very, very big object. And as it traverses through from the center of the sun out towards the edge, it loses much of this energy. And much of these photons that started off as gamma rays, time they reach the outer edge, they are now within the visible light range. And as long as they're in the visible light range, evolution has it that us and other animals have developed the ability to see visible light, to basically invisible light. So we've got certain cells in our eyes, and those cells that connect to our brains that allow us to interpret these particular photons. So, I mean, it could have been that we at some stage couldn't recognize visible, wasn't one of those things, and maybe we recognized radio, and maybe and in fact some animals can see better than humans. Humans sort of can see, I think, from 430 nanometers to about 700 odd nanometers, and that's all you can see. And yet there's some animals that can see further than that and less than that, so they can see higher frequency than the 430 so they can see beyond both of those. So in the infrared, if you like, area, and in the ultraviolet area. So, but we humans, we can't. So we don't have that facility. Maybe there's some humans who can. Maybe these humans who see ghosts. Maybe that's the thing. Hey? You know, when they see a ghost and stuff like that. Maybe these are special humans that can see beyond the infrared. See, I'm starting a whole new conspiracy.
You are. Well, if I can just jump in for a second there. We're talking a lot about the quantization of energy, and and sort of photons being discrete packets of energy. And one of the discussions that led to this idea that there are only a limited number of energy states that a photon can have was the ultraviolet catastrophe, right? And for the benefit of those in the audience, this is the study of black body radiation. The whole term black body radiation comes from analysis of energy inside a very dark oven with a very small hole in the side so that you can see what's going on. And they quickly worked out a bunch of theory that seemed to work at the high frequencies and seemed to work at the low frequencies. But when they combined these theories, it turned out that the oven would produce infinite energy. and that's why it's called the ultraviolet catastrophe. And people got desperate to try and answer this, try and find out with a way to explain it. And it was up to Planck, who eventually came up with the idea. Well, actually, energy can't exist at all frequencies. It can't exist at all energy levels. It can't exist at all energy levels. It comes in very discrete bundles, and that's where that's the other way. When you talk about gamma rays being individual energy levels, that's another side of that coin. Would you agree with that?
Yeah, absolutely. That's precisely it. But what's important is that we have evidence of this. So in other words, we didn't just make it up.
Yeah.
Okay. All right. So now let's just have a look at. So why, by the way, why do they call it the electromagnetic continuum? Let's have a look. So basically, we've got just basically go over this. I think everybody's seen this 1,000 times. Again, very, very long wavelengths to very, very short wavelengths, and somewhere around here, a very, very thin slither of that is visible light. So when we're talking about gamma rays before, talking about wavelengths that are way out of here, extremely powerful energy over here. Very low frequencies over here. So over here we've got things that this can be as much as a kilometer. All right, that wavelength can be as much as a kilometer when we're talking about radio. And when we're looking at stars and stuff like that, we generally are looking at it around this area here, over here. Okay, so radio. So when we talk about a telescope, for instance, you could have an optical telescope that uses this range. So that would be an optical telescope. So Flat Earth is saying, well, how can you see those stars out there? That's just CGI. You can't be seeing those stars out there. You can't see what those stars look like optically. Well, actually, you see, visible light, radio, it's all the same stuff.
Yeah.
Okay. It just depends on whether your camera can pick up this or your camera can pick up this. For instance, the camera, the all 16 channels on the Himawari 8, all might pick up different lots of this. All 16 channels will pick up different wavelengths over here, different slots.
Yeah, and I think that's.
But
Yes, they are all photography. I mean, it's just, and here, sort of when people talk about electromagnetic radiation, the 5G conspiracy nuts do it as well. When they talk about electromagnetic radiation, they instantly assume that electromagnetic radiation must be harmful. But light is just a form of electromagnetic radiation. It's not. There are some forms of radiation that are harmful.
Well, those ones be after ultraviolet. We've got once we've got violet, then we've ultraviolet. A, B, C, and then once we get into ultraviolet C and beyond that, those are harmful. And the reason that they're harmful is because they have enough energy effect. And as soon as they can do that, as soon as they can ionize atoms in your cell, ionize. Remember, I spoke about sodium, about its lonely little electron whizzing around near its extremes. Well, that's easy to lose, especially for sodium. Okay, so sodium will very, very easily lose this electron. In fact, anything in group 1 of the elements have this one single electron. Very easy to lose this. Okay, so sodium loses this electron. This electron is combining with something happens.
Yep. So it's and that's got to do with the wavelength, right? The wavelength, whether or not an electromagnetic wave can interact with the human body cell is critically dependent on the wavelength of the radiation, right? We talk about, and we use radiation actually in a misleading sense, because alpha particle is considered to be radioactive decay, but that's just a helium ion, really. It's not. It's not and de Broglie would say that this is just a form of radiation. It's just a form of energy radiation. But from my perspective, actually, alpha particles and beta particles, they're actually particles. They're not just electromagnetic radiation. It's a.
They have mass.
Yes, they have mass. Mute Rap asks, could we give a simplified explanation of how photons are created? And my argument is no. Photons are photons are axiomatically the packages in which energy travels from one point to another. And that's axiomatic. There's no more fundamental precedent. Anyway, sorry.
All right. So let me again. I like to talk about evidence.
Yep.
Okay. All right. So what is the evidence that light behaves as a wave? So apart from the obvious, which is which we know now about electromagnetic radiation and how that behaves.
Mm-hmm.
And how we have solid equations backed by experimentation.
Yep.
That gives us the wave formulas. For instance, the gamma, which is C over H. So, where have I put that? Okay. Yeah. So anyway, what is the evidence of that? Well, one of the most famous ones, with I think all the flat earthers seem to know about this bit of evidence, really understand what the ramifications are. Double slit experiment.
This blows my mind.
Yes. Okay. So just looking at so without looking in the details of whether someone's watching it, whether someone's not watching it, the fundamental thing is that given a plate that's got two slits that are incredibly close together. Now, if you, for instance, when we actually have to try and to make this happen in a lab, this is very, very hard to do. Okay, that's because you can't get these slits close together. What I do is I actually use an old-fashioned razor blade and cut and use the razor blade to cut the slits.
Right.
And have to use a magnifying glass to get those slits close enough together. Mm-hmm. Okay, so that's not an easy thing to do, using the razor blades. And I use the razor blades for diffraction, which is another way of getting these slits very, very close together. Yeah. Now, what happens is if you're shining a light source through these slits, so we'll probably use a monochrome, say a LED of a particular color. Mm. So we use monochrome so that it's not confused with different wavelengths of light. So might be a green laser or a red laser. So you've only got one wavelength to be concerned about, and then over here, as it shines on your screen, it produces fringes. So you got light, you got dark fringes and light fringes. Mm-hmm. So that's what this produces. Okay, so here we have photons coming over here and producing this array of fringes.
Yep. And this,
you're saying, well, how the hell does that happen? What causes this to happen? Because even if I just shot one electron at a time, one photon at a time, I still get this fringe.
Let me just, so when we first saw this effect, when we first saw it, okay, you shine a light through the double slit and you get the fringes. Everybody said, okay, light is a wave. No argument. This is the evidence for it. This is proof. Because each of those slits is a source for a wavefront, and those
Yes.
wavefronts propagate out from the slits. They interfere with one another, and they make these light and dark shapes on the screen at the end, and therefore we can tell that light is definitely, absolutely 100% a wave.
Well,
And
not
then,
maybe.
and then they decided, well, what happens if we do it one photon at a time? And that's
Yeah.
where things get weird.
Okay. So yes, that's where the if you were watching it, it did one thing, and if you weren't watching it, it did something else.
Yep.
But what's important here in terms of the evidence, I just want to stick with the evidence just for a minute. Why did we think that this was a wave? Just because of those fringes.
Yep.
And that is because the waves create constructive and destructive interference. So where two waves come together, the crests come together, the wave gets bigger. So those fringes in the middle are actually brighter. So the wave gets bigger. And where a crest meets, it cancels the wave out altogether. There's no wave. So therefore you get the dark fringe. So you get the bright fringe because the waves come together, called constructs. So they join together, making it even brighter than a single wave on its own. And at the same time, if they cancel each other out, it's dark. You end up with a dark fringe part of it. Now, this idea was used later on to make these fancy earphones with noise cancelling.
Yep.
Because hang on a second, if we can do this with light, we should be able to do the same thing with sound. And of course, what happens with noise cancelling is that your earphones actually listen for the noise that's outside, and then reproduces that in exactly the same but out of phase, so that the reproduction of the noise from your earphone and the noise that comes from outside cancel each other out with destructive interference. Yep. Exactly what happens here.
Exactly. And
okay, and therefore that's why you pay so much money for these
even
things,
helicopters
having do this accurately is difficult to do.
Even helicopters can do that. They can reduce their noise signature by having by producing an out of phase noise signal that significantly makes them quieter. It's got military applications, but it's it's exactly the same principle as you say.
Okay, and therein lies your evidence.
Yeah.
Okay. All right. Oops, I just dropped my paper.
That's okay.
There we go, I got it. Okay, all right, so evidence of that, the Rayleigh criterion. So Rayleigh talking about diffraction, again, misunderstood. So I watched a show from that nut, actually, scammer, Oakley.
Yeah.
Okay, so this is just an outright fraud, fleecing people, right? There's no question about it. I don't believe for 1 minute this guy actually thinks the Earth is flat.
No,
actually, I doubt any of those of the flat Earth gurus actually believe that nonsense.
There are certainly some of them who seem to. I mean, the more prominent ones. Dell seems fairly convinced. Darwin seems fairly convinced.
Yes.
But Brian's logic seems convinced. But I wouldn't describe any of those as either astute or mentally healthy. But Quantum Eraser and Nathan Oakley certainly seem to be scam artists.
No, exactly. That's just outright. Look, and well, good luck to them if they're people who want to pay them, to listen to nonsense. Good luck to them. I just have a view about some of the people who I would call them victims.
Yeah, okay. That's the thing.
So they can't participate in the advances of science because they've become victims. So now everything is a conspiracy.
Yeah, And once that happens, they're prone to any other snake oil salesman. It has been funny to watch Oakley be systematically corrected and educated by conspiracy cats on the subject of diffraction and what it can and cannot do. My question about this is, where is this double slit? You're talking about this object going further and further away. Where is the double slit causing this diffraction?
Okay, so all right. So basically when we're talking about about this double slit experiment, we've got a screen here that's, as I mentioned, putting two slits together like this. But then we can actually predict these fringes and predict the distance between those fringes and how many fringes based on the wavelength of this particular source of light. And this is what gives us the evidence. So not behave exactly the same way. How they behave relates to their wavelength. Now, we spoke about how light is a wave. Well, how is light a particle then? And what evidence is that?
Mm-hmm.
Well, here it is. So Einstein actually came up with wrote, if you like, most of the work for the photoelectric effect. So here we have a metal plate. Okay, and let's say this plate is 100. And we have this connection. And we have a source of light. So let's call it a LED. Say it doesn't have to be monochromatic. It's light coming from the sun. And we have photons that hit this plate. And the amazing thing is, for every photon that hits this plate, it releases an electron. Now, all we need to do is find a way to collect this electron, like we would in any normal voltaic cell. All we're actually doing is collecting the electrons, and it's this movement of the electrons which produces the electricity that we can use. So, as the light hits the plate, it kicks off an electron. So we can now use this electron, to run whatever we want, electric thing that we want, or save it in a battery. So this shows us that light must be a particle in order for that to happen. Okay, so there's more evidence of light being a particle.
Yep. And you can also observe radiation pressure. Like when we do satellite orbits, when we calculate satellite orbits, the effect of radiation on the course of the satellite is actually non-negligible. There is because of the impact of the radiation. From that perspective, the radiation is acting like it's made up of tiny particles that are hitting the satellite and exchanging energy with it. So there are multiple levels on which this is electromagnetic radiation has photonic characteristics.
Yeah, well, not only that, we're at the stage where we can actually count the photons. Yep. Okay, so we know how many photons there are, and knowing how many photons there are, we can predict exactly how much electricity we're going to get for a given amount of light.
Yeah.
Okay, and we can actually prove that the inverse square law because of this.
Yep.
Okay, we can actually use this to prove that. So again, flat earthers, it's all about evidence. We don't just say there's a firmament and not provide any evidence for it.
Yes. And it's we have, and it's not just one form of evidence. Once you've got, it's sort of, it would have been very easy to do the double slit experiment with lots of photons all at the same time, see the dark light patterns, and say, okay, well that's it. We know as much as we need to know. Light is just light. The electromagnetic radiation is clearly wave-like, and we can move on. We don't need to consider it. But we didn't do that. Well, scientists didn't do that. They went back and they said, well, what if we do it differently? And then what if we do it differently again? And what if we do it differently again? And you ended up with this bizarre sequence of results that didn't make sense from a single perspective. From the perspective that light is definitely a wave, or that light is definitely a particle. It didn't make sense from either of those. It had to have the potential for both, and it's a really, really, really interesting interesting process, but it drives you to, in order to understand what's going on, in order to understand the result of that real world experiment, your mind needs to go down some very unintuitive paths.
Yeah. Anyway, I was so we were just my wife was just tidying her up yesterday, and because we're doing a little bit of renovating, and then came across something I had a long time, and I've got 2 volumes here. I don't be pretty hard to see what they call, but I can tell you they call the chemical analysis quantitative Fresnius is the author, and these were presented as graduation, because as I told you, my initial degree was in chemistry, right. So I majored in chemistry and mathematics. So I did a double major, and that started my life off as a chemist. And this was presented to me. And by the way, these were written in the year 1900.
Oh wow! Yes, and still remain accurate in many of their details. I would think, not necessarily, not necessarily up to date in many respects, but this is the thing about knowledge. We build on layers of knowledge. There's a lot in there that is still absolutely 100% reliable.
So back then in 1900, all right. Remember, this was written in 1900. They had already made chemical equations. So many things. I can look through this and see exactly what their thinking was at the time and how this worked. We're talking about people who were alive then, like Bohr, okay, and Planck. People who were actually working in the field right then, and how their work was incorporated into a work like this. So incredible, just reading this is like reading a history of how chemistry worked. And the thing about it is, I guess one of the beaut things about this was that this gives you detailed information on how to do things the old-fashioned way. Like when you did a chemical analysis, you had to actually do what's called wet analysis. In other words, measuring out, creating standards, measuring out small amounts, producing graphs with your own hand. And of course, even when I first entered the world of chemistry, this is the way it was. And this is what I loved about chemistry, that you had all the tubes and the liquids and the bubbling and squeaking and all that. I loved all of that stuff. But in a very few short years, after Varian came out with the spectroscopy,
yep.
Life changed for all of us, because this turned out to be a method of analysis that we just could not match with the old-fashioned way of doing things. So very quickly, chemistry turned from all of this beautiful stuff with tubes and glassware pressing a button. And that's kind of where I sort of fell out of love with some of the with work in the laboratory, because I didn't want to stand behind a big machine, just pressing the button and recording, it's the absorption.
Yep.
Okay, so this book over here, and I still use that if I'm with students and I say, look, I'm going to show you how this was done before, um, you know, before all of this came into being, so that you can understand how this actually works, and in fact, what the machine is doing for you.
Yes. So it's a and I do want to stress here that sort of there's a lot about the 1900 the view of how physics worked, the physics of atoms and subatomic processes, that was not well understood back in 1900. But that
Yeah,
doesn't mean that anything that was developed before 1900 is useless. And we constantly get in. Well, I find it frustrating that Oakley goes on about 100-year-old, 100-year out of date model for gravity. It's not out of date. It works perfectly well in the range of circumstances it was intended to work for, the Newtonian theory of gravity. We build on top of previous work. We don't just turn around and say, well, that's completely useless, it'll never be touched again. That does happen sometimes, but it's like phlogiston theory or whatever. But
yeah,
it's very, very unusual for that to happen. One of the things that it did happen with, however, was the ether. um, uh, because light was considered to be a wave, it was considered for a while that there must be an ether, there must be a medium that it's traveling through.
yeah.
But then we did experiments and we worked out no, as far as we can tell, there isn't one. Yeah, again, it gets back to your central point that every time we have an idea, we go out and we say, well, how can we check this? How can we verify it?
Well, there is a proviso there,
Mm-hmm.
Tony, and that is we could be
We could
wrong.
be, yes.
Okay, we could be wrong
Yep.
about it, and but for flat earthers and that to assert that there is something there is an ether, and that just assert it with no evidence at all. That's not how science
Yep.
works. If we're wrong, evidence will produce the reason for why we're
Yep.
wrong.
It,
If we're right, evidence will show
yep.
us right. So far, there's no evidence of
Yeah.
it, and you can't suppose that something exists if you don't have evidence for it existing.
Yes, and I think that the key element is the sheer hypocrisy of flat earthers, right? If science operated the way that they suggest that it should, like you have to personally do an experiment in order for that experiment to be valid, nobody would get anywhere, right? I mean, science would be at a pathetically limited state because there's just so much great science being done by all sorts of people. And, if the whole idea of publication is that you can use other people's results, you do need to check them, and you have to check other people's results. There's a famous example of Louis Pasteur, who published a paper about how you could tell two different molecules apart. He was talking about isomers of lactic acid. Like an isomer is a different geometric. They
Yeah,
have a handedness, and and there was a theory. How is the handedness of lactic acid? Are they all right-handed or are they all left-handed? Is there some distribution? What is it? And he did this experiment where he crystallized it, and they went through and they picked out the crystals with different optical properties, and they worked out that it was about 50-50. And so he published this result, got it into a journal, and then everybody tried to do the results and couldn't do it. They could not
yeah,
repeat his results. And so this caused a scientific controversy. So they went back to his laboratory and they did it, and it worked. And it turned out that the process he described only works at the humidity and pressure and temperature conditions that apply in Paris in
Yeah.
spring.
Well,
And you know we do check stuff. We check whether or not, and when it doesn't work, when there's no idea, when we can't reproduce, we want to understand why that is. It's a really complicated and important process, and flat earthers want it to be simple, didactic, and they want, sometimes they want observational evidence, and then other times, I'm not sure if you heard Nathan Oakley rounding on somebody who was suggesting that he might want to send up a balloon to check what conditions were like at the top of the atmosphere, and Oakley just went off his nut. He was so angry. Like, what would we be verifying? There's nothing to verify. We've proven everything. Well,
yeah, that's right.
you
Exactly. So
think you've proven everything, but you might want to actually go check, mate. But anyway.
Well, I think that shutting people down is purposely done.
Yeah.
And the reason for that is because the more that you introduce questions, the more that people who think the Earth is flat ask questions.
Yeah.
The more that they realize that this idea about this flat Earth is nonsense. For instance, this misunderstanding about the second law of thermodynamics, which is just words they throw around as if they even know what it means.
Yeah.
But the point is that why, first of all, the question they could ask themselves is, why does a gas particle move at all?
Yeah.
What causes it to move?
Yes.
And what could you do to stop it from moving?
Exactly.
What could you do to change its direction?
Exactly. And that's...
So ask yourself that simple question.
Yeah.
And if you ask yourself that simple question, then you'll say, right, okay. So if the question is, why doesn't all the gas particles go off into space? Well, ask yourself, what would stop it from doing that?
And they've got...
Well, it's pretty obvious. It's
yes,
gravity.
That's right. And I'm not sure exactly how flat earthers decided that gravity has to not exist. And I've been working on this video. Sorry to go into a segue. I've been working on this video about helium balloons. Why do helium balloons come up? Because it is a question that flat earthers ask, and I got to the point where I said, well, this is about as sensible as suggesting that an Olympic weightlifter can hoist up 300 kilograms of weight. Therefore, there's no such thing as gravity. It's exactly the same argument. There's an upward force applied to the helium balloon, just like there's an upward force applied to the barbell. It's exactly the same. There's no difference.
In fact, yes, exactly. The upward force is exactly the same as you can actually measure it, and as okay. I mean, surely that's a question that somebody who facts would ask themselves.
Yeah. And I mean,
so basically, we're having particles that are displacing these as they head down. They push other things up. That are left. Another question: why don't ask themselves? Why is it 122,000 feet is the maximum that it'll go?
Yeah.
Why can't it go? Well, it's a very simple thing. By the time it gets to 122,000 feet, the density of the stuff outside of the balloon for the same volume in the balloon is the same, so it can't move any further. How is that not evidence to you?
Yes, Jessica was just asking me when did I invite Moses on the screen, because I've hidden my luxurious beard because I'm a beardsman. Simple conservation of energy gets us there, right? You're moving upwards against a force. As you do, you lose kinetic energy. Therefore, you lose the energy that you need to move higher. You need energy to move upwards. You don't have an infinite amount of energy. And the same, the same's true. So I had somebody say, gravity can overcome entropy. Entropy is not a force. Also, objects cannot have infinite entropy. This is a misconception. The fact that the entropy of the universe is constantly increasing does not mean that it is infinite, right? Because entropy, the way I prefer to look at it, is the amount of energy no longer useful to be done for work. So because the universe started out with a finite amount of energy, it can only ever achieve a finite amount of entropy. Entropy keeps on increasing towards that upper limit, but that doesn't mean that it increases indefinitely. It just increases until everything is at maximum entropic state. And as long as the universe is finite, which at this stage it seems to be, entropy cannot be infinite. And certainly the gas pocket in an atmosphere cannot achieve infinite entropy. It just doesn't happen.
Yeah. So just one last thing that I wanted to talk about with light was the idea of the sun. So again, this is directed at those people who think the Earth is flat and that the sun just goes away from you.
Yeah.
Right. So when you're looking at the sun and it's going away from you, they said, well, presumably it gets smaller and smaller, which it doesn't, by the way.
Mm-hmm.
But it should, if your hypothesis was correct, that it's just going away from you. So if the sun would go further and further away from you and get smaller and smaller, their idea is they don't need it anymore because it's too small.
Yeah, that's right.
But you can see the damn stars over there, can't you?
Yes.
Why is that? You can see the stars all the way there in the same direction that the sun supposedly went.
Yes.
What's so special about the stars that you can see their light, but you can see the sun?
Yes. And I mean, sort of the idea that you reach the diffraction limit, where you can't tell, where the human eye is unable to tell individual light sources apart. There's no, that doesn't explain the bottom of it doesn't explain stuff that you observe, like the sun halfway below the horizon. That cannot happen because of that. Like a ship halfway below the horizon. That cannot happen because of that. What you're telling me is that the photons from the top of the vessel aren't undergoing this process, but the photons from the bottom of the object are. And it doesn't matter if it's the sun, the moon, a ship, whatever. There's no reason for the bottom of it to be so much more heavily impacted by this process, whatever you are ascribing this process to, than any other, than the top part of the star. It doesn't make any sense. The angular distance between the top and the bottom is not so large that you expect different effects.
Yeah, exactly. So I'm not sure if can.
I will bring you back up to the. I will give you the screen. So give me one moment. Yep, you're on screen.
So one of the reacting, and there's a guy called Gary Wyben, been picked up by Oakley and QE. So what they say is the diffraction limit that creates this phenomenon where we can't see the bottom of this and we can't see the bottom of this one. So what they're saying is that the more that this is compressed, and the reason that you can't see it is because it's compressed. I just already described with light as in terms of pretty obviously, if you're looking at things, let's say, for instance, like this lighthouse, that's got the bands on it, and Jose had one of these perfect like this on his
Mm-hmm.
show, and he showed this. If this was compressed, they say it is, then it wouldn't look more.
Yep.
This same lighthouse, if you like, first of all, because it's compressed,
Yep.
and secondly, these would be much
Smaller.
would be large, smaller as they approach the
Yeah.
water. But they don't.
They don't. And I mean, you can see, there are images of ships where they have, huge writing on the side. The writing doesn't get distorted. The writing doesn't get compressed. It remains perfectly legible right down to, and I forget what. Yeah, right to the horizon, and there's a beautiful image where you've got multiple ships with these with the same markings on them, and they show that the further ship is being obstructed. It's not being compressed. It's not being made fuzzy. It's not being diffracted or anything like that. It's just an idiotic the entire thing, and they clearly can't use these technical terms in any sort of meaningful fashion. Oakley's nonsense about things diffracting into the distance. The object.
Yes, this exact thing. That's what he's saying. So he's saying, well, yes, things will, the diffraction limit will happen for things in the distance. So as you get further away, you won't be able to tell two peaks apart. That's fine. We understand, but that doesn't apply here. You can see this as clear as day. You can see that they have not. I can pick out these bands with no problems at all. Yeah. So why is it that I can't pick up the ones that are near the water?
Yeah. And again, you're getting back because you're a scientist. You want to get back, and you want to get back to the observational validation, and they will make a statement like, well, the reason that happens is because of diffraction. Okay, prove it.
Yeah, exactly. Just use the word. Yeah. That's all they do. Just throw around words like thermodynamics and diffraction, and in fact they bear no resemblance to the reality of what's happening.
Yeah.
But the point is, what they do is they throw these words around, and then these words get repeated.
Yes.
By other people who have no clue themselves. They don't understand why they're using the words. They just throw, oh, that sounds like a scientific word, so I'll just use it, and therefore. But they don't actually know why it is. What gets me is what's going on in their noggins, in those heads, that would accept this and not want to question it. I don't get that.
Well, I think sort of there's a lot of I think there's a lot of psychological a lot of psychological need to be better. And sort of flat Earth offers this thing. I have this insight. Everybody else is so stupid. I am so much smarter than everybody else because I question this stuff. I am not a sheep. I do not follow. I accept what's told to me, and it makes them feel good. And I suspect that most of them, require that. Need some emotional protection as to why it is that they haven't achieved what they wanted to achieve, why their life isn't consistent with the fact that they're one of the brightest people on the face of the planet. That's just my theory. I think that's a huge part of it. Is just emotional cushioning as to why they haven't achieved what they think they ought to have achieved. There's a conspiracy out there that hides the truth, that hides my brilliance, and I'm part of the truth seekers and the and you know the geniuses that are finally seeing the truth.
Yeah. So Tony, are there any questions out there from the peanut gallery, as they say?
There were a few, and normally I was Rachel's been confronted a few times, and she's talking about the moon.
Okay.
She still has questions, and I mean she seems. I got frustrated with her a few weeks ago, but we've sorted it out soon.
So what's the question about the moon?
Well, it's a question for flat earthers, actually. I just need to find it. Sorry. Okay, S. Thurston, on the other hand, has a question. When the probability wave state collapses, the interaction has imposed the collapse to a random state subject to the probabilities, no mind involved at all. Yeah.
Statement, yeah.
Yeah, that's a statement more than anything else. Uh,
So I guess one of the things that here we are preparing for another attempt at a moon landing.
Yeah.
By the way, the Chinese Space Agency 3 days ago
Yep.
have sent a probe to a lander, which so what they're going to do is they're going to actually drill this time, and they're going to actually collect the samples.
Yep.
They're going to bring them back. So they actually have a spacecraft. The lander is going to be able to take off from the moon, and the orbiter is going to actually bring all of this back to Earth. And these have agreed to share their samples with the rest of us. So that'll be interesting itself.
Okay, I have found Rachel's comment. She saw a video of a solar eclipse from an airplane, and the shadow moving, which she thinks proves that the moon is solid and the sun is further away than the moon. And she now has some questions about light and phases. Just to clarify, so we talk about the phase. Does she mean phases of the moon?
Probably.
Okay. All right. So there you go. All right. That was her question. That's the question she's got. I think that my 2 cents is Gary Y. Benger's alternate account. Gary Y. Benger is blocked on my channel because he's an abusive dick, and I don't put up with abusive dicks. So if you want to be unblocked, that's I'm sorry. I don't. I don't have to put up with people whose only purpose in life is to come in and abuse me. I don't have to, and I won't. So if that's your only reason for being here, Gary, do it somewhere else. I don't care. And you can go and complain to your friends in the flat earth community about how I'm a big meanie and I censor people. Don't be a dick. I have blocked a bunch of Globers because they came onto my channel and they were dicks. I don't put up with it. Do it somewhere else. Yep.
Totally
and now that I
unnecessary.
know who your alternative character, your alternative account, you can bet that it's going to get blocked too. So,
you can chase your tail, Tony, doing that because they can create unlimited ones.
Well, that's true, but I'll just block them all, and it takes a lot longer to create an account than it does to block it. Colin asks, wouldn't it be possible to measure the length of the blades on the windmills and calculate optical aspects from that?
Oh, that's a brilliant question. Actually, I'm just going to do this. So the board back up. That's definitely a good question, and this is that flat earthers can do. Okay, if what they believe in is true, then carry out this experiment. So, if you see objects, let's say, and you'll see that that they have different heights, and so on. And the reason they have different heights is because they have different distances. Okay, so here we have these windmills. On a map, these same windmills will have different distances. Like this one will be that far. That one. This one might be there. Might be a bit further, and this one much further away. So that might look like this on a. What we do is to get this distance. So work out what this distance is, the angular distance here for every one of those windmills. Okay? So here's your graph, and you're going to plot height. That's the height of the windmill, and you're going to plot the distance to the windmill. Okay, so we'll call that 0. This is where you're standing. Now, plotting these with a graph that looks like this, the Earth is flat, no question. These windmills were deliberately put in the sea at different heights, which is nonsense. So, if this turns out to be a circular function, so that y squared is equal to r squared minus x squared, it will be, by the way, then the Earth is a sphere. This is an experiment you can do for yourself. It's quite easy to do.
Exactly.
So come back with your plot, see if it matches y equals mx plus b, or whether it's y squared equals r squared minus x squared. Let's see which one it is. If you care about what you believe in is true, go and do this experiment. Because this is definitive proof of whether the Earth is flat or whether it's a sphere.
It's a and this is, there's a lot of, so if you look at your top formula, y equals r squared minus x squared, so y is equal to the square root of r squared minus x squared, this you can approximate that using the 8 inches per mile squared, or which the flat earthers often go for. But the formula for a circle is so simple that there's really no reason not to use that. Unless you're doing lots and 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 lots of calculations and observations, there's just no reason to use the shortcut. It's just not accurate.
Okay, so let me just interrupt you there, Tony. There's one other really good point that you can actually use your data to work out what the radius of the Earth actually is.
Yes, exactly.
So that's another good reason for doing it. You can actually see how close you can come to the reported radius of the Earth. By the way, those people who say no one's ever measured the curve, well, are satellites out there whose only job is to map the Earth. That's what Light Cartosat 3.
Well,
and every single time this satellite takes a sweep, it compares what it's got with the radius, the diameter of the Earth.
So
every single time it's measured.
It's a there are things like there are various satellite-based systems that can be used to determine the relative positions of ground-based stations, like GPS. The French have a system called Doris. There's satellite laser ranging, which we use to determine the positions of the laser ranging stations. And there's very long baseline. There's a thing called very long baseline interferometry that involves looking at the phase differences from distant quasars at various radio telescopes around the world. and they can use this to work out the distances of the network of radio telescopes. It's very information intensive, but there are just multiple techniques. A lot of them ground based, a lot of them satellite based. That that we use all the time to investigate the shape of the Earth, because it's very important. Understanding where stuff is relative to other stuff is actually incredibly important, and we use it to map the motions of continental plates, or work out which areas on Earth are more prone to earthquakes. If you've got in Indonesia, for instance, I had some colleagues who were looking at the motions using GPS to analyze the motions of an island. I might just bring myself up for so that people can see my incredibly illustrative hand gestures, because you're missing out on half the story there. So they were looking at this Indonesian island, and they could see deformation over here and deformation over here, but no deformation in the period in the middle. And so they said, well, actually, that thing in the middle is obviously blocked. It's got tension is building up there, because it should be moving to accommodate the motion at either end, and it isn't. So this is a high risk area. This is a high risk earthquake area, and an oil company came along, built a pipeline through this, and then there was an earthquake exactly where the people said it would, that disrupted the pipeline. These high precision techniques actually have very good real world applications. The flat earthers just deny that any of this is happening. It's insane.
Well, yeah, I think that is insane. It's a good way. Anyway, I think we've reached our
allotted time. Yep, that's okay. Right. I must apologise again. I've been feeling quite unwell this week, so I overslept. I'm sorry, and I didn't get the notice out to everybody, so viewership was a little bit down. My apologies for that. But apart from that, of course, it was a triumph of professionalism and technical proficiency from beginning to end. Anybody who says differently is just wrong. I will sue them. I will sue them in court.
I've certainly improved it. So what do you want to talk about next?
You were suggesting that we might want to do a couple of episodes on light. Do you want to consider? Yes. Do you want to consider light again next week? Do you want to change it up?
Yes. Why not? Okay. Well, let's have for those people who are interested in the science. Yep. I'd probably go further into some of the equations that we have, and how that works, and probably explore the evidence a bit further.
Yep. I think. So I'll that sounds like a great idea, and
we'll do some real world examples.
Mm-hmm.
Pose a question and then answer it.
All right. And again, if people do have questions that they'd like answered, please just leave them in the comments below.
That's a good idea. Let's do that as well, and answer some actual questions as well.
Okay. But we might let Phil Bell get about his day. Thank you, Phil, very much for being here. Thank you, everybody in the chat. Jessica G, Rachy, Fohammer was here but had to go. Jim's Mind, the Mute Donkey who was asking a lot of questions. There's Bren.
Ask him to put the questions in the chat, then we'll answer them.
All right. Jessica G says, great show, Phil Bell. Thanks for coming on. You're a student, the annoying older guy. He needs to shut his mouth more often. Okay. But I'll talk to you anon. And thank you, everybody, for being here. I really do appreciate it.
No worries. Bye, everybody.
I just need to...
Okay.